Okay, so an ideal gas in a sealed container with a fixed volume. Person heats up the container so the temperature goes from 293 Kelvin to 310 Kelvin. What's the corresponding increase in pressure if the original pressure was 241 pascals? So I want you to go ahead and set this up. Go ahead and draw it out and set up your variables and see if you can figure out what the increase in pressure will be. And again, you're looking at the ideal gas before, ideal gas after, and seeing what cancels out from both sides and doing that. So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so we've got our gas, temperature 1, 293, temperature 2, 310, pressure 1, 241 pascals. And we can cancel volume from both sides. Volume's fixed, so same volume on both sides, same number of moles on both sides. Ideal gas constant's the same for both, so we're looking at a ratio of the pressures and temperatures, and we end up getting a pressure of 254.98 pascals. So again, with dealing with the ideal gas law, we can combine all these different relationships into one, where the pressure and volume is directly proportional to temperature. So pressure times volume is directly proportional to the temperature. And then in terms of the amount of gas present, the temperature, pressure, and constant volume is proportional to the amount of the gas. Then we have the relationship with the mass as well here. So if we're not introducing more mass into the system or taking away mass, we can consider that there. So in terms of using number of moles, this could be a really, really helpful thing for us. And so 1 mole of an ideal gas has the same volume. And so, 1 mole occupies the same space. The number of moles, number of molecules in 1 mole is the same as well, and that's really helpful for us. And so when we talk about what's going on with atomic theory, that's important to consider with this too. The atomic and molecular masses are measured in the unified mass unit. So 1 U is 1.6605 times 10 to the negative 27 kilograms. And so let's figure out the mass in kilograms of 1 H2O molecule. And we can do that here. So we want to find the atomic mass, and we convert that to kilograms. And so we have our values here, we have oxygen here, we have our hydrogen here, and we have our, water molecule here, one oxygen, 2 hydrogen. And yeah, so if you can see if you can do that. What's the mass in kilograms of 1 molecule of water? So go ahead and pause the clip and try that, and when you're ready to check, you can hit play to continue. All right, so the atomic mass, you have 2 hydrogens, you have 1 oxygen, so the amount in U is 18.01528 U. 2 oxygen or 2 hydrogens, 1 oxygen, and we convert to kilograms, and we should get 2.9914 times 10 to the negative 26. What you basically do is you set up your bracket here. You've got U, so 1 U is 1.6605 times 10 to the negative 27th kilograms. So in 2011, we had the earthquake in Japan that was very devastating, and they had the explosion at the Japanese reactor. And I'm not sure if this link still works, but you can Google search that and read about the nuclear reactor. And so essentially what happened there directly relates to what we're talking about with the ideal gas law here, where you have pressure building up so much, and it's contained, and then when it can't be contained anymore, it's open to the open, and so that those radioactive particles are released into the atmosphere and get on substances, and it can be pretty yucky. And so it's important to consider the the gas laws for a lot of different things, including safety with nuclear reactors. So this is K9. What we want to find out is what is the mass in kilograms of an O2 molecule. So this will be good practice here. Go ahead and pause the clip, give this a try, and then when you're ready to check, you can hit play to continue. Okay, so we've got Yeah, H2 or O2 rather, 2 oxygen molecules, so 32U. We convert to kilograms, so 5.314 times 10 to the negative 26 kilograms for that. Okay, now the mole. The mole is defined as the number of grams of a substance that is numerically equal to the molecular mass of the substance. So, in other words, if we had 1 mole of H2, right, 1 mole, so here's a container, and in this container we have a lot of these molecules, right, a very specific amount, we'll talk about that. And then H2 has a mass of 2.02 grams. So that is how much, if we had a gas, right, this gas, and we put it on a scale, and we would read that, we would have 2.02 grams is how much that would be. And the way we got that, if we know what hydrogen is, this is 1.0079 U, right? We have 2 of those. We have the corresponding grams. And so in other words, like with this, we have this is U for neon, right? That's the atomic mass. So therefore, if we have a mole of that, right? And so I should kept it the same size as this, right? So same size, and we have all of those neon molecules inside, right? 1 mole of that, 1 mole of neon is this many grams. And so if we put it on a scale, we would read 20.1797 grams because of all those different molecules in there. If we have CO2, it's 1 carbon, oxygen, 2 oxygen atoms, right? So we add those up in U, and so that container would have, you know, we measured it, would have 44 grams of mass. And that should make sense because every mole has the same number of molecules, the same number of dots. There's the same number of dots in here, same number of dots in here, same number of dots in here. Each dot represents 1 molecule. And so therefore, if you have the same number of molecules, each molecule has a different amount of mass, and so therefore, you know, if you have the same number of CO2s as you have H2s, right, you're obviously going to have more mass, and so that's what we're dealing with there. So the number of moles in a certain mass is, or the number of moles in a certain mass of material is this relationship here, and so hopefully that makes sense there. So a mole is defined as the number of atoms in 12 grams of 12 carbon. So 1 atom of this is 12 grams. Okay, so let's take a look at this for F10. And let's say we want to find out the mass in grams of 3 moles of fluorine gas. So here is 1 mole of it. Here's another mole of it. And here's another mole, right? So in these 3 moles, how much mass is there? How much mass? And so in fluorine, right, fluorine is F2, and so we can do that. So if we want to know how many molecules there are, and here's Avogadro's constant, this is the number I was alluding to earlier. In 1 mole, right, if you have this gas inside, you have all these dots, each of these dots represent a molecule, okay? In a mole, in 1 mole, this is how many molecules, that's how many dots you have. That's how many dots you have. So if you have H2, let's say, right, H2 gas, then that's how many H2s you have in there, right? Or fluorine, right, fluorine gas, F2s, that's how many F2s are in there. And so this is the total number of molecules in 3 moles, right? And that's for any gas, right? So it could be for H2, for F2, oxygen, you know, O2, whatever, okay? So once we have that, you know, we know that we can multiply that by 2, and you know, for 3 moles, right? So 1 mole would be that. That would be how many molecules are inside. So in other words, that's how many dots you have in there. But every single one of these dots, if we look at one of these dots, that means that we have 2 atoms of fluorine, right? So if we have 2 atoms of fluorine, this is the total number of atoms. We have to multiply this by 2 because each of these dots again just represents F2, which are 2 separate atoms that are sharing electrons, right? So that's the total number of atoms. And then if we know that, and we know that fluorine is this value in U, we multiply that by U, and we get that mass, and then we can convert that to kilograms. Now, what's easier than that is just noting that, okay, you know, in 1 mole, right, in 1 mole, we have this many grams. But the trouble is it's F2, right? So we would multiply this by 2, and that's how many grams that we would have. And so that's a little bit easier way to go about it, but it's important to know both ways. So when we take a look at the ideal gas law, PV equals nRT, where N is the number of moles, R is the gas constant here. And this is the typical unit that we'll use. We're dealing with Kelvin, right, for temperature. Joules, with joules, you're going to be dealing with meters cubed for volume, pascals for pressure. And so this is typically what we'll use there. Some useful facts that we can have with this. The standard temperature and pressure, we're going to be using a 0 degrees Celsius, 273 Kelvin. The pressure in atmospheres is 101,000 pascals. 101,300 pascals is 1 atmosphere, ATM. The volume of 1 mole of an ideal gas is 22.4 liters. So in other words, a mole that is at 0 degrees is all going to have the same volume. So this mole with, you know, all those molecules inside is going to have this shape, right? Which is also this in meters cubed. So in other words, 1 times 10 to the negative third meters cubed is the volume of an ideal gas. And if the amount of gas does not change, then we have, you know, this relationship there where the ideal gas before should equal the ideal gas after. This is just missing, you know, N and R, right, on both sides, because both sides have the same number of moles. We can cancel that, divide that from both sides. R's divided from both sides. And those are previous examples we had that. We must have kelvins for temperature, and then pressure must be absolute pressure. Okay, so 3 moles of CO2 are enclosed in a sealed container, 40 centimeters by 25 centimeters by 15 centimeters. If the pressure is 1 atmosphere, what is the temperature of the gas in the container? So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so here's our gas, PV equals nRT. 1 atmosphere is 101,000 pascals. Technically 101,300. Either way is going to be okay. It's going to be plenty close. The volume is 0.015 meters. That should be meters cubed, not meters squared. We'll set everything in there, and we should get a temperature of 60.73 Kelvin. So this would be very, very, very cold if this was the actual situation there. Okay, on this one, we have a 2-liter container that has 4 grams of H2, 132 grams of CO2. The container's temperature is 35 degrees Celsius. What is the pressure inside the container? So go ahead and pause the clip, see if you can solve this one. And when you're ready to check, you can hit play to continue. Okay, so CO2 is 40 to 44 U, so 44 grams for 1 mole of it. H2 has 1.00794 times 2, so 2 U. So therefore, 1 mole of that gas has 2 grams. So we know we have 132 grams of CO2. If we divide that by 44, we actually will find out that we have 3 moles of it. And then for H2, it says we have 4 grams, so therefore there's 2 moles of that because every mole is 2 grams for H2. So we have 5 total moles, and that may have been the toughest part of this one here. From there, we can figure out the volume. 1 liter is 1 times 10 to the negative third meters cubed, so that's the volume in meters cubed. Temperature needs to be in Kelvin, so we get that in Kelvin. PV equals nRT. We should, in the end, get a pressure of, what would that be there? 6,402,550 pascals. Okay, so using the ideal gas law, using the conversion with moles and grams, and then also looking at volume here in meters cubed. So I'll get there. So yeah, so hopefully all that solidified there for you.